Welcome all of you for the fourth lecture on gravitation. So in the last three lectures we have spent a fair bit of time trying to understand the basic laws of dynamics, basic laws of motion, both kinematics and of dynamics. And then we also discussed the nature of fundamental forces and how gravitation is a very important fundamental force because it binds all objects on the macroscopic scale. It binds us to the earth, it binds the solar system together, and it holds the galaxy together and galaxies also together. Gravitational law and its formulation essentially involves a knowledge of distances between bodies which are very, very large. So we are speaking of the distance between the earth and the moon, the earth and the sun, so on and so forth. And it also involves a knowledge of the masses of the objects. So when you solve your problem, these pieces of information are given to you. When we formulate the law, it is very important for us to know how these quantities are initially estimated and later determined with greater and greater accuracy. So with that in mind, I spent a couple of lectures discussing how using trigonometry and some assumptions on the behavior of space, that is, it satisfies the Euclidean postulates like such as the sum of the three angles of a triangle is 180 degrees, so on and so forth. We can actually determine distances, and it has been done by astronomers for more than 1500 years. The determination of masses is a much more delicate job. In fact, masses are determined through the law because we cannot take a weighing pan and try to find out what the weight of the sun or the moon or the earth is. So I will come to that later. So what we shall now do is to assume that we know how to determine the distances and then proceed to formulate the law today. Today's lecture is probably very important to you because we are going to see the logical structure in the formulation of the gravitational law, how we can combine the Galilean law of freely falling bodies, which I discussed at great length in the last lecture, together with Kepler's laws. The point is that we are combining one terrestrial law. The freely falling body is done on the surface of the earth, maybe a few hundred meters at most, and Kepler's law refer to planetary motion around the sun. So we are going to combine these two and then formulate gravitational law with the help of centripetal force, which is something that you have learned in your previous classes. So it is very, very important. So at this point, we should not forget that Galilean law involves a very, very important concept which I call principle of equivalence. Namely, gravitational charge is equal to inertial mass. So please remember, this word charge is used in a general sense. Your K, the spring constant, is like a charge. Your magnetic moment is like a charge because it gives you the strength with which a body couples to a force. Conventionally, the word charge is not used. It is replaced by the word mass. That is how the principle of equivalence is formulated. So we say gravitational mass is equal to inertial mass, which means that the acceleration of a body, at least in the Earth's gravitational field, is independent of its mass. So I gave the example of a freely falling stone and a block of lead which was performed by Galileo from the Leaning Tower of Pisa. We have to remember that. So what we have to now do is to formulate Kepler's laws. So, if you look at the screen, you will see the formulation of Kepler's law. I have already discussed the equivalence principle. Kepler made use of the elaborate tables prepared by Copernicus and Tycho Brahe, and he tried to find a pattern. Trying to find a pattern is not an easy thing because it assumes an intelligent choice of coordinate system, and in the Ptolemaic model the concept of a coordinate system was very, very complicated. So, what is Ptolemy's picture? You have the earth, you have the sun going around us, the planets going around us, the stars going around us, so on and so forth. It does not matter which of them represents what. Now, the initial assumption is that it is going around in a circle, but then you find observations do not agree with the idea that it is going around in a circle. After all, if you look at the night sky and if you look at the motion of a planet like Saturn or Jupiter, they do not even appear to move in the same direction. So, with respect to Earth, Saturn may be appearing to move in this direction. Let us say this is the Earth and this is Saturn. After a while, you will actually find that it appears to move in the opposite direction. So, this is what is called as retrograde motion in astronomy. In Indian astronomy, this was called Vakri Gati because it is not moving the way it should be moving. So, the solution given by the Ptolemaic school was to say that, well, this is moving in a circular orbit. At every point, there is another circular orbit around which moves. So, every point on this main circle acts as a center for another circle. So, now you can keep on building more and more circles around every point. You can build a circle around this point, so on and so forth. And each of these new circles was called an epicycle, and a very elaborate model was built. And basically, if you want to completely describe the trajectory of a planet, you need an infinite number of such epicycles, at least a very, very large number of such epicycles, which are out of much use, because these are merely geometric constructions which do not give us any insight. However, this was the model which was followed by astronomers in the ancient days, because there was a firm belief that the Earth is at the center of the universe, very much as humans are at the center of evolution of all living objects, living beings. A radical departure to this actually was taken by Kepler. So, the formulation of Kepler's law first of all assumes a heliocentric model. When I speak of a heliocentric model, I am not speaking of a model where the whole universe is going around the sun, however attractive it may be. Our purpose is very limited, and what we want to say is that planets are moving around the sun. So, it is very tempting and it is very convenient to assume that the planets are moving in circular orbits with the sun at the center. Of course, it is only an assumption, and careful observations should either verify it or overrule it. So, I will put a question mark. So, what is the first thing that Kepler did? He shifted the center of motion from the Earth to the sun. That is very, very important. So, this is a heliocentric model for planets. By the same token, it will be a geocentric model for the moon. We assume that the moon is going around the Earth, and the Earth in turn is going around the sun. That is the assumption that we have to make if we want to understand Keplerian law. So, if you try to fit the observed positions in the sky of various planets, what Kepler found was, so we are discussing Kepler's first law. orbits are only nearly circular. They are not exactly circular orbits. That is what Kepler found. So, what are they? Kepler knew enough of coordinate geometry and geometry. So, Kepler was able to fit all the orbits to elliptical trajectories. These are nearly circular. We are not looking at orbits which are highly elliptical. They are the farthest planets. We are looking at Mercury, Venus, Earth, Mars, maybe Jupiter and Saturn. So, they can be fitted to elliptical orbits, and you know that an ellipse, I am drawing a exaggerated figure, has two focal points. So, this is a nearly elliptical orbit. Sun is slightly shifted from the center, and this is the position of the Sun. An important point to notice at this juncture is that when I speak of an elliptical orbit or an elliptical trajectory, ellipses are closed orbits. So, orbits are closed. The big question is, are they really exactly closed? For that, you need even more precise observations, astronomical observations, which cannot be done just with the naked eye. The answer is no. There are perturbations even around the closed orbits. That is not of any interest to us at this particular point. They can be understood by refining the law of gravitation to include the perturbation coming from other planets, so on and so forth. So, at this point, we shall assume that the motion is completely elliptical. It is a closed orbit. So, we have formulated the first law where Sun is one of the focal points. Now, I have to come to the second law, which I am going to state. So, what you do is, I am not going to worry about elliptical orbits. I am going to look at circular orbits. So, assume that the Sun is somewhere here and the planets are moving in a circular orbit, and you ask what is the angle subtended by this object over a certain interval of time. That is what you are going to ask. Now, if you ask what is the angle subtended is the same in equal intervals of time. So, that means that it covers the same arc length in equal intervals of time. So, if this is theta and it is t, this is theta and it is t, the same distance is covered, which means that it covers equal area. So, the planet sweeps equal area. So, what do I mean by that? In equal intervals of time. So, let me show that schematically. If I look at this area and call it A1, and if I look at this area and I call it A2, then A1 is equal to A2. What Kepler found was that this is true even when the planet is moving in an elliptical orbit. When the orbit is circular, your angular velocity is a constant, whereas when the orbit is elliptical, the angular velocity is not a constant, it is going to change. So, what Kepler found was that the velocity always adjusts such that equal areas are swept in equal intervals of time. So, this is the second law which I will formulate. The second law: equal areas are swept in equal intervals of time. Please notice that the motion is not circular, it is elliptic. The angular velocity is not a constant, but still equal areas are swept in equal intervals of time. There is a third law which Kepler discovered, which is the most astounding law and which is very, very important for us. The second law is also equally important. Kepler found a remarkable universality. So, a remarkable universality for all planetary orbits, or for all planetary orbits, and let me formulate that. So, we come to the third law. Okay, maybe I should use blue pen, and that is, so let us say that, so this is not a good figure. Let me take circular orbits, that is a simpler one. So let us say that the sun is situated at the center. So this is a circular orbit for a planet 1. This is a circular orbit for planet 2, so on and so forth. So we are formulating the third law. Now let us say the planet 1 is a distance r1, the planet 2 is at a distance r2. In an elliptic orbit, of course, this distance is not fixed, it is going to change with time. So there we are going to speak of the mean distance. So you calculate the distance at different positions and calculate the mean distance. The mean distance is a constant for a circular orbit, but the true distance is not the same as the mean distance for an elliptical orbit. There will be some small variations because these ellipses are not highly deformed, they are nearly circular. That is what I told you. And let the period taken by planet 1 be t1 and let the period taken by planet 2 be t2. So for example, you can take r1 and t1 to be Mars, r2 and t2 to be Jupiter. Mars is an inner planet, Jupiter is an outer planet with respect to the sun, because Mars is much closer to the sun than Jupiter. What Kepler discovered was that while for different planets the periods and the distances change, there was one quantity that was invariant. That is why I used the word universality. So irrespective of which planet you are going to choose, you find that t squared by r cubed is equal to constant. T squared by r cubed is equal to constant. Later, when you people study the Bohr model, in your next year, you find another constant of this same kind, which was a mysterious number in spectroscopy, that was called the Rydberg constant. And Rydberg constant gave birth to quantum mechanics, the Bohr model and the whole of quantum theory. In a similar manner, we are going to show how the third law, which says that the ratio of the square of the period to the cube of the distance from the sun is a constant, gives rise to the formulation of the third law. So we are in possession of these three laws, and it was verified to a very great accuracy. So it is a very thrilling result, but now the question is, how do we understand these three laws? So what we have at our disposal is excellent observations, and universal patterns common to all planetary motions, common to all planetary motions. And how many universal patterns did we see? 3 patterns. Ellipse, equal areas in equal times, and thirdly t squared by r cubed is equal to constant. Whenever there is such a universality, remember Jupiter is very big, Jupiter is much more massive, Mercury is a very small planet, almost gaseous, Earth is quite a solid. So in spite of all that, if all of them should depict the same behavior, as always, a good question to ask is, if there is such a common underlying theme, their motion must be governed by a common law. And this is this law which Newton set forth to find out. And of course, there is a fourth one. These three are patterns, I should say, plus one result. Namely, all these were independent of the mass of the planet. Mercury is very light, Jupiter is extraordinarily heavy. You can probably put 12 Earths in Jupiter, so it is so big and so heavy. It's almost a star, so to say. But still, we find that their acceleration is independent of their mass, and then they move in elliptical orbits. The bodies sweep equal areas in equal intervals of time. I have just now explained that to you. And finally, there is this funny relation that the square of the period of a planet divided by the cube of its mean distance is a constant, and we have to understand that. Obviously, the way to understand is through the concept of a force. So what we have to do is combine kinematics. So all these are kinematical results with mechanics, rather dynamics. Kinematics is about trajectory, acceleration, angular velocity, angular acceleration, position, etc., etc. Dynamics is about force. And let us remember the two important laws that we are going to use now. The first law is, of course, of not any interest to us because there is a force acting. If there were no force acting, all the planets would have been moving with straight line orbits. So we would never have been able to see the same moon again and again, or Jupiter, or Saturn, or Mars. So remember the second law, which says that dP by dt is F, where P is my momentum. And the second law is also very important. The force acted upon by A on B is minus the force acted upon by B on A. So this third law of motion is essentially a statement of conservation of momentum, we told you. So what we are going to do now is to make use of the two laws and try to understand what the common underlying theme is. So this will be our mission for today. So let me sort of give you a brief summary of what we are going to do and what we have discussed so far. So the first thing is that the motion of the kinematics of planets is independent of their mass. Kepler employed the heliocentric model for the planetary system. Let us not worry about the rest of the universe. Then he discovered the three laws. That is what we had. What we now want to do is to make use of all the laws together with independence of mass, make a simplification and try to get at the gravitational law. So that is why I have highlighted the word simplification. So what is the simplification that I am going to do? At this juncture, I am going to ignore the fact that they are elliptical. I am going to assume that they are spherical. We are not going to lose any generality in that to get the law, because once you get the law, you can always verify whether that law correctly gives you the elliptic orbits. Once an object is in a circular motion, we know that if you use the second law, equal areas being swept in equal intervals of time is tantamount to constant angular velocity, and that is tantamount to a centripetal force, a uniform centripetal force. So we will make use of that. Then I am going to make use of the third law, and deduce precisely what the nature of that force is. So now you see a full-fledged interaction between kinematics and dynamics. So this is something which is truly enjoyable, and that is what we want to do. We are also going to use the third law to establish a reciprocity. So let me explain that. So please stare at the screen for a while. I have written something in a very cryptic form which I am going to explain by working out. So what I am showing here is that suppose a body A, so let us call it as a planet A, has a mass ma, and a body B has a mass mb. What are we saying? We are saying that the force exerted by A on B is the negative of the force exerted by the body B on A. But in gravitational case, when A moves in the field of B, its acceleration is independent of ma, and when B moves in the field of A, its acceleration is independent of mb. So let me write that here. So there is a planet A and there is a planet B. This has a mass ma, this has a mass mb. So what are we saying? Newton's third law says F A on B, when I write this arrow, A is acting on B, is equal to negative of F B on A. So I will put a vector sign, although it is not very important at this particular point. The acceleration of A is independent of mass ma. The acceleration of B is independent of mass mb. So what will I do? First I will look at F B upon A. So I am asking for the force exerted by B on A. What should this be? This should be proportional to ma. How do I know that? This must be proportional to ma because this is nothing but ma into its acceleration, A of A. Now if it is proportional to ma, when I equate these two, the proportionality constant goes away and my acceleration of A is independent of its mass. So the force that is exerted by B on A is proportional to ma. Now let us make use of the symmetry, which is essentially what the third law is. My force on A because of B should be proportional to mb, but then they are negatives of each other. So what are we going to write? We are going to say that the force, whether A acts on B or B acts on A. Now I am not interested in the sign, I am only interested in the magnitude. It must be proportional to ma into mb. That is the statement. This is very, very fundamental, and we already got a very nice description of the strength part. What is the next thing that we are going to do? The next thing that we are going to do is to make use of the circular orbit. So let us remember the kinematics of the circular orbit. So if I have a circular orbit, at any given point my velocity is tangential and the force is radial, is inward radial. This is my force and this is my velocity. So force is inward radial. The acceleration is always in the direction of the force. Therefore, my acceleration is also inward radial. Both are inward radial. If there were to be a centrifugal force, that would have been outward radial. Centrifugal force is an inertial force, it is a pseudo force, it is not a real force. But here we are speaking of real forces produced by real bodies, and that is a centripetal force that is inward, so we know what this is. But when I say that is inward, I only fix the direction, I do not fix the magnitude, I do not fix how it changes with the distance. So what do I know? I know that it is proportional to ma. I know that it is proportional to mb. I know that it is inward. So what do I do? Let us say that I locate the center of the orbit at the origin, and this is my circular orbit. I need not have written a three-dimensional figure, and this is my unit vector r, then my radius vector r, my f is proportional to minus r. Only then it will be inward, and my acceleration will also be proportional to minus r. Plus r is this direction, minus r is this direction. This is f, this is minus f, if you feel like. So this is something that we have to remember. So how do I write the force now? I write my force to be, so let us say I locate my body A here, and locate my body B here, and the radius is f. My f is nothing but minus g, that is a constant of proportionality. Then I will write a mass of the body A, mass of the body B. I am looking at the force exerted by A on B. So I have already written this, therefore I will put the unit vector r, and then I will multiply it by an unknown function f of r. This corresponds to the centripetal force. So what is the condition on f of r? My f of r is greater than 0, because the sign has already been accommodated. Well, if you want to call this Ra and if you want to call this Rb, then you will have to define Rb minus Ra and write its negative. That is what I have done in my slide, in my computer slide, but never mind about this. We have almost got the law. So what we have done is to consistently and repeatedly use the second law, the third law, the Keplerian law, and the concept of centripetal force. So now if we can somehow determine this f of r, bingo, we have got the law of motion. And what is it that we have left out? The only law that we have left out is the third law of motion. So we shall invoke that here. So that is what we have to do. So what we have to do is to make use of the third law. Okay. So what we are going to do is to assume that it has a certain dependence. Even otherwise it can be found out, but it is convenient to assume that f of r has a certain dependence, and then we will deduce what Kepler's third law is. So our mission is determination of f of r. So let us say that f of r is proportional to r to the power of n. Of course, Newton said that it is proportional to 1 over r squared, n equal to minus 2, and that is what we have. Actually, I am going to return to Kepler's second law to get equal areas, 15 equal intervals of time. Through this again, the centripetal force automatically guarantees that. We will do that in a while. So let us see what the argument is. So I will show you the basic things that I have written on the slide again, and then I will work it out. So here the left hand side is my centripetal force. My right hand side involves the unknown function. I am looking at an orbit with a fixed radius, so everything is absorbed in k. I want to cancel my m, I have kept it. I know the relation between angular velocity and the period, and I am going to use that in order to determine f of r. So this is a snapshot of what I am going to prove, and here I am going to work it out in great detail. So let me write that down. So what do I have? I have my force is equal to m omega squared r. I am assuming a circular orbit. Because equal areas are 15 equal intervals of time, my omega is a constant. Let us not forget that. That means the period is a constant too. And this quantity is nothing but, we are only writing the magnitude. We are not worried about the direction anymore because I have already declared that it is a centripetal force. So this is m, and this is the mass of the other object. I am sure you people can figure out. Then there is a g, I have already written that, and then I have my f of r. So that is what I have to write, and I have to equate them. So this is the statement that the acceleration is independent. I can combine this, the mass of the other object and g, into a constant k, because we are looking at the motion in a given period. Therefore, what we have is omega squared r is equal to some constant into f of r. So we have incorporated the second law of motion and the circular orbit. What I have to now do is to employ the fact that omega is equal to 2 pi by t. So what does it imply? This implies omega squared is equal to 2 pi whole squared by t squared. So let me substitute. So what are we saying? So we are saying that omega squared r was a constant into f of r, and this tells me that 2 pi whole squared r by t squared is equal to constant into f of r. So in other words, r by t squared is some other constant k prime into f of r. That is what we found out. Now what do I have to do? All that I have to do is to argue that t squared by r cubed is a constant. I have r into t squared, so what shall I do? I shall multiply it by r squared, and I shall multiply it by r squared and make it constant. Because this quantity is nothing but r cubed by t squared. If t squared by r cubed is a constant, r cubed by t squared is also a constant. It is nothing but the reciprocal. So this is what I have. So what does it imply? This implies f of r into r squared equal to constant. So we have to box it. We have to box it and frame it in a golden frame, because we are almost on the verge of arriving at Newton's law. So if f of r into r squared equal to constant, what do we conclude? We conclude that f of r is proportional to 1 over r squared. That is what we conclude. So if f of r is proportional to 1 over r squared, there is a constant of proportionality which can be absorbed in g. Therefore, what does it imply? This implies my gravitational force magnitude wise is nothing but g ma mb by r squared, which is exactly what Newton wrote. So now I can complete this argument by also fixing the direction. So let me fix that. I have this. My body A is here, my body B is here. So this is RA. This is RB. This is RAB. So we are showing the vectors correctly. Then, so my F, this is A and this is B, the body. F A acting on B is minus G MA MB by RAB squared, that is what I have, into unit vector RAB, which is probably the most celebrated law in physics, This is the universal law of gravitation, which we shall now extend to all bodies having masses. So, we started with the Gallean law, which looked at freely falling bodies in the Earth's gravitational field. Then we looked at the planetary motion. Now, what we are going to do is to say that what is valid at the terrestrial scale and what is valid at the celestial scale should perhaps be valid at all length scales. This is of course a generalization, an assumption, some kind of an inductive argument, and we will postulate that this law is the correct law which is valid between any two massive bodies, irrespective of what the distance between them is, irrespective of what their masses are. That is a very, very important thing. That means a final vindication of the formulation of this law will come only when gravitational law is verified at all length scales with bodies of varying masses. At this point, I would like to caution you people that although the argument is so straightforward, so simple and so convincing, it almost looks like a derivation of Newton's law. Please remember, this is not a derivation. This is only a motivation. Like all fundamental laws, this law also cannot be derived. It is an extraordinarily important thing, and that is why it is called as a law. Law of conservation of energy cannot be derived. It is a fundamental law. You can formulate it. Law of conservation of momentum cannot be derived. Maxwell's equations, which you are going to study, the Coulomb law, the Biot-Savart law, these cannot be derived. Ampere's law, they cannot be derived. They are fundamental laws. That is why we call them Maxwell's laws, laws of electrodynamics. In a similar manner, law of gravitation can also not be derived. These equations are set up. What do we mean by set up? You make a number of observations and you ask for the simplest and the most convincing logical way of formulating them. And if we are lucky, nature accepts this formulation, which we will verify by looking at phenomena that take place in the laboratory or in the sky at various levels, and that convinces that this law is correct. So, for example, if you have an inquisitive mind, you should be able to ask, how do I know for sure that this law is the same when I look at two bodies which are separated by a micrometer? You could ask that question. In a similar manner, you could also ask the question, how am I sure that if I make very, very careful measurements, that this law is accurate even at the astronomical scale? For example, I told you in doing this, we assume that the orbits are closed, but the orbits are not closed. So, if I look at the motion of a planet, for example, it is not only acted upon by the sun, it is also acted upon by the other planets, because of which the orbit need not be closed. So, a big question is, what would happen if I took all the effects into account? Do I get a complete agreement, or is there a mismatch? So, what I am trying to emphasize is that physics is a continuously evolving experimental science with which the theoretical construction or the formulation tries to catch up. So, that is exactly what happened when Einstein gave his general theory of relativity. He found that the orbit of Mercury, there was a small discrepancy, very, very tiny discrepancy, which could not be explained by Newton's law, and he had to actually develop a brand new theory. In a similar manner, we should be able to ask a question whether there are variations in the gravitational field over a micrometer scale or a meter scale. There are occasions when people claim that they have actually found such a variation, but luckily those claims have not been substantiated. So, it appears that gravitational law is quite robust around this length scale. Of course, if you go to extraordinarily small scales, gravitation probably will get a correction. It is getting a correction at the galactic scales, but still you see that the sweep of gravitational field is enormous. Let us say from a meter to hundreds of thousands of kilometers, and there is no wonder that Newton called it the law of universal gravitation. So, what we have done is to set up a law using everything that we know, and at this point we should not forget the genius of Newton, because he formulated every single concept that was necessary. The laws of motion, the concept of inertia, he made use of the centripetal force, and he formulated the law of gravitation. And it is for this reason that Newton is considered to be probably the greatest physicist that humankind has ever seen so far. However, there is a small reconciliation that we have to do. We have not yet completed that. Once we did that, we are ready to work out applications, and that should actually be the end of the discussion of gravitation as far as we are concerned. So, what is the reconciliation that I have to do? Let me see if I have a slide on that. Okay. This is the formulation that I have written. I have written it slightly differently here. I have put a cube, the distance between A and B in the denominator, and I have put the full vector, whereas when I worked it out, I put a unit vector here and I put a square. Usually it is called the inverse square law, and that is what we have done. Okay. Now, the reconciliation is that the minute I write F is equal to minus g m by r squared, let me not worry about the vector sign, force is falling with the inverse square distance. So, let us say that you have a very massive object, earth, and there is the proverbial apple which is falling. So, apple is falling towards the earth, and what is apple? 3 meters, 4 meters, so that is the height. So, let me write another figure. So, I have the earth and there is a tree and an apple is falling. So, we are speaking of something like 10 meters, let us say, maximum. I mean, we do not find an apple tree which is 10 meter tall, but let us say somebody went on the top of a building and dropped. What is the thing that we find? We find that this acceleration is a constant. It is independent of this height. But Newton says that it should fall as the square of the distance. Therefore, we have to reconcile the Gallean law, which says that acceleration is a constant. That is why you denote it by g, acceleration due to gravity, with the inverse square distance, and that is a very easy thing to do. So, let me do that for you, and then we will see what the other applications are. So, what are we saying? I am going to draw an extraordinarily exaggerated picture. So, my center of the earth is here, the radius is r, and an object is falling radially inwards, and this distance is h. So, even this figure is not to the scale. Therefore, at any given time the total distance is r plus h. This is the total distance. This appears to be very simple, but actually this is one of the most complicated concepts. What is the complication in this? Earth is an extended object, it is not a massive object, whereas in my formulation I always showed the body and body to be point masses. I was able to define a distance. Now, let me draw another picture. If my earth is here and if my body is here, which distance are we supposed to calculate? This distance, this distance, this distance, this distance. In fact, what we should do is we should look at the force coming from each of these massive small units of mass, and we should be able to find out, and we do not have the wherewithal to do that. I do not know how to integrate basically, and it might interest you to know that even Newton did not know how to do it. Newton invented differential calculus, Archimedes invented integral calculus, but Newton did not know how to do this integration. Of course, it is very, very tempting to say that when the earth is going around the sun can be taken to be a point object, but I cannot take the earth to be a point object when a stone is falling from a 100-meter tall place. I cannot do that. So, Newton did not publish his years for almost 15 or 20 years because he wanted to prove that whenever there is a spherical distribution of mass, we can assume that all the mass is concentrated at the center. So what are we saying? This is a very, very important result. It follows from what is called as Gauss's law, which you will study in your 12th standard. So let us say that there is a uniform spherical distribution, uniform mass density of radius r. Now, if I look at an object which is sitting somewhere here, okay, and this distance is r, the question is, what is the force on r? The force on r is as if all the mass was concentrated at the circle, at the center of the sphere. So, the force is given by G m by r squared, where r is the distance from the center and this is the total mass. So, what are we saying? This m is rho into total volume, which is nothing but 4 by 3 pi r cubed rho. You are given a uniform mass density. This small m is the mass of this object. R, small r, is the distance between this center of the sphere and m. You have to prove this. And Newton did not know how to prove this. And being a very honest person with very high standards for himself, he did not publish the result until he gave a proof for this. He gave an extraordinarily beautiful geometric proof. We will not worry about that. It is too early for you at this stage for us to give this proof. So, if you are going to make an assumption, now we can reconcile the falling body problem. Falling body. So, what is my force? My force, rather my acceleration is nothing but minus g mass of the earth divided by, I need not worry about minus also, r plus h whole squared. So, this is what I have. And what are we saying? We are saying that h is much smaller than r, because r is the radius of the earth and h is the height above the center. So, what is it that we have to do at this particular point? Very simple. We have to make a binomial expansion. All of you are familiar with binomial expansion. The 0th order approximation that we can do is to say ignore h. So, 0th order approximation, since h is much less than r, take h approximately equal to 0. That is not a nice statement to make. Take h by r approximately equal to 0, because it is a very small number. Then a is given by g m by r squared, which must be your acceleration due to gravity. So, we have already reconciled to a certain extent how we are able to get a constant acceleration, and this is the number that is given to you to be what? 10 meters per second squared, 9.8 meters per second squared, so on and so forth. So, if you know the mass, you can find out the gravitational constant. If you know the gravitational constant, you can find the mass. But then we can do better than that, as I told you, by making a binomial expansion. I would like to discuss that. So, probably, since that would take a little bit more time and you people would like to revise whatever we have done so far, let us stop at this particular point and resume our studies with the law of falling body, and then go on to look at applications involving satellite motions, artificial satellites, escape velocity, so on and so forth. Bye.